C to the n, e to the minus I, e n over h bar times time, times psi n of x. Everybody agree? Yep. And then we just went through a procedure on how to find the CNs. What is that called? Yeah, the Fourier's trick.
We're multiplying by psi of n.
You multiply by psi of n on both sides, and then you integrate. And you exploit the
Delta function.
the delta function or the orthogonality of the basis functions that came from separable solutions. And they're square normalizable. Okay. It's all nice and consistent. All right, and we've done that now. We've done example problem 2.2. What was the other? 2.7. And then my example. All right, so we've done 3 example problems of this for the infinite square well. Okay, so now the next question is, once you get this, then what? You've got a nice idea of what the total wave function is. All right? What's the next thing that you want to do?
What CNN is.
Okay, well, we've already done that. So we've already gone through and we've done that. We've got the nice expansion. So then the next question is, we have to calculate things like observables. Remember observables, where we have the operator and we calculate expectation values? For example, we might want to calculate the expectation value of energy, of position, of momentum. Okay, and how do you do that?
Calculate, you can get probabilities.
Okay, so you use the probability. Remember the idea from the probabilities?
Mm-hmm.
So let's say we want to calculate the expectation value of some operator. All right, and that operator might be momentum or something. I'm making it general.
Now you have to take the integral of psi of general times the operator.
Yeah, okay.
You have to multiply that by the complex conjugate as well, or?
Yeah.
Well, let's try it out. So I agree with you. The integral. Let's start with the integral.
Then we write the psi general, but we
Star.
star sign.
Yeah, psi general.
Star. And
Star.
You
Yeah.
sandwich that O in between that and another psi operator.
Very good. Exactly.
Dx.
Then dx. Okay. So how the heck would you do this, guys?
We did that already.
Well,
What's that?
We did that.
Well, we did this, but not for the big general side. We did it for the stationary state solutions.
the little psi, right?
So we've got to plug in this mess into here. All right? So let's do that. That becomes the integral, and let's write it like this. The sum over n of Cn star e to the plus I En over h bar t times psi n star, then operator, and then what?
Summation of just that without the stars.
All right, but can we just write it as summation over n? Like if we were to write it out, right? You don't just have like psi 1.
So you'd have to summation over m.
Very good, Jeremy. So these are the steps that you need to be taking. And that's a silly thing, but that's right. You have to realize that this becomes a summation. You have to use another dummy index. Right? So very
Right.
good. To see all that.
That's what I missed before, so this is good.
Good. So you saw it. You had been thinking about it, and it was sitting in the back of your head, and this is the answer. So then it would be Cm e to the what? Negative
I.
minus I Em over h bar t times psi m dx.
And Cn and Cm, so constants would come out.
Okay, so let me try to reduce this a little bit. So this is going to equal, I'm going to break it up. I'm going to break this up into the integral of the summation of n equals m. So I'm just going to look into the n equals m terms.
Going to delta function.
Okay, very good. So David, you're starting to anticipate it. It's going to be the Cn star of e to the plus I en over h bar t times psi n star, then operator, then Cn e to the minus I en over h bar t times psi n dx. What happens to the time-dependent part?
Can't take that away.
All right, now let me add the next term. So then it's going to be the integral of the summation for n not equal to m. All right, and that would be the same thing. So it'll be the Cn star e to the plus I en over h bar t times psi n operator Cm e to the minus I en over h bar t times psi n dx. Okay, working on this, we can reduce this down to the, it's going to be
Squared.
the summation over n of Cn squared times the integral of psi n star operator psi n dx. All right. Plus, I'll write this as the summation of n not equal to m of the integral of a whole bunch of stuff. All right. But part of that stuff is going to break down to psi n, that should be star, operator psi m dx.
And that second term goes to is 0 because n is not equal to m.
Okay, for psi n and psi m, well, for psi n's equal eigenfunctions of O, this term goes to
0.
it goes to 0, because this reduces down to, this comes up, this brings the eigenvalue out, and when you bring the eigenvalue out, you have the integral of psi n star psi m dx, but n not equal to m, and that's the delta function. And as a result of the delta function, it means the n and the m's are orthogonal. So what happens to that integral?
Goes to 0.
It goes to 0. So this thing goes to 0. And then what does this come out to be? Well, now this is the operator. So this pulls out like the operator. So this pulls out the eigenvalue, On.
So operator is 1.
So this equals the summation over n of Cn squared times On, where this is the eigenvalue. Okay. So we now have the expectation of this operator equal to this thing.
Those are baby size, or those are baby size, right? 'Cause
These?
yeah,
Yeah, they're spatial
yeah,
people.
because the time fact, we did the time thing, right?
Okay, so what does this remind you of? Reminds you way back to when we did discrete probabilities, right? And when you had to calculate the average or the expectation of discrete probabilities, right? You gave probability times the value, remember?
Yeah.
When going back all the way to that grade problem, when we calculated the average grade, it was the probability of the given grade times the grade. All right? So this is like the grade. And so what do we recognize this as?
That's the probability of the grade.
Yeah, so exactly. So we
C
recognize
squared
this
probability.
as the probability.
And it says our side, the integration, it becomes 1. It's just Cn squared times 11.
All right, the point that I'm trying to make here is that these projections, way back here, if you square those projections, what do they amount to?
Probability.
They kind of amount to the probability that if you made a measurement on this whole system, that you would find the state being the nth state. So look, you have a 1D infinite well, and we have this initial boundary conditions like what it started with. And what we found out, that the total wave function is some linear combination of all those stationary states. For example, n equals 1, n equals 2, n equals 3, n equals 4. And what we said is, what we found out of the CNs, which were the projections of how much the state was in a given one. For example, what it was the problem that I did? Example. The problem I did was that psi of x and t equals 0. So this was the initial condition for an infinite square well, was something like this. Remember?
5a, negative 5a.
Yeah. Yeah. Right? And then when we went and we found the CNs, right? The CN was biggest for which thing? So, the n equals 2 case. Very good. And the n equals 2 case was this one, right? So C2 equal the max. Right? Because that kind of looked like this. Alright, so if C2 equals the maximum and I squared C2, that's the probability of being in C2, what state would you most likely measure this system to be in if you were to measure C2? You measure C2. Could you find it in one of the other states, like C4, C6, C8? You could, but what would be the probability?
Less than.
It's less than. Alright. What's that?
Less than 1.
It's always going to be less than 1, right? Less than or equal to 1, because probability has to equal 1. But I think in the book they did a nice example, and again, I just did a different example. But in example 2.2, do you remember what example 2.2 was? The initial condition looked like what?
Ax times a minus x.
Okay, so for example 2.2, what did the initial, it looked like this, right? If you plotted it?
Yes.
Yeah.
Okay, so what basis eigenfunction, stationary state, all the same thing, the stationary states are the eigenfunctions. Which one should be the biggest?
A over 2.
Which one? So with the solutions, psi 1, psi 2, psi 3, those are the stationary states.
A times a squared over 4.
Okay, so again, I'm not quite sure what you mean, but
The value
remember that what we found out of the stationary state solutions were psi 1 of x and then psi 2 of x.
So I want to have the highest.
That's right. So C1 should be the biggest, right? And example problem 2.3 follows example 2.1 and shows that C1 squared is 0.9985. Okay? So let's stop here and let's get rid of any questions. Because I'm seeing some faces that are nodding, and I'm seeing some faces that are not nodding. All right?
0.9985 sounds very probable.
Okay. And does it kind of make sense? Okay. So let's see if we can put the whole story together once again. We have an infinite square well, and we solve for a complete basis that's square integrable. I know I throw a lot of words in there, but I'm telling you the precise word. With this square normalizable per complete basis, it means it's Hilbert. Right? It's a Hilbert space, and it has all the properties of a function space. So therefore, we have the orthonormal conditions between the bases, right? Which means that the dot product looks like a delta function,